Hey guys, Mr. Longbrake here again. I hope all is well and you guys are still staying safe. For this lesson, we're going to focus on potential energy diagrams. And potential energy diagrams are a graphical representation of a chemical change or a chemical reaction, where our heating and cooling curves that we covered earlier in the unit were diagrams or graphs representing physical changes. This is going to be a diagram that represents the energy exchange in a chemical reaction. And the particular chemical reaction we'll use as an example today is hydrogen plus oxygen yields water. So just a simple equation to help us understand what these graphs are all about. And we need to know all these different parts and pieces of the graph. First, let's just make sure we know that the x-axis is time, so as time goes by, and here is going to be potential energy, and usually that energy is going to be in joules, which is abbreviated by a J. Sometimes you'll see kilojoules, which is kJ, or sometimes you'll see kilocalories. And you guys have heard calories before with food items, and sometimes you'll see that unit as well. But all of those are units of energy, and that will be on the y-axis. Okay, so the first thing we need to know is where is the potential energy of the reactants, or what on this graph represents that. And this first horizontal line is going to be the potential energy of the reactants. It's how much energy is stored in the bonds of those reactants. So the energy stored in hydrogen and oxygen to start. And so if I were to ask you what is the potential energy of the reactants, it would be 40 joules for this particular example. All right, next we have the potential energy of the products. So we know from our previous slide that this is where the reactants are. Well, our products are just on the ending horizontal line, so the very end of this potential energy diagram. And so that is where our product will be, or the potential energy of the products. And the potential energy of the products is the energy stored in the bonds of the products, so how much energy is stored in H2O or water. And if I were to ask you to give a numerical value for that with this graph, it would be 20 joules. Okay, next we're going to talk about a very important term, and that term is called activation energy, and it is abbreviated or symbolized with a E subscript A. That means energy of activation or activation energy, and it's the amount of energy absorbed in the particular reaction. And that amount of energy absorbed is signified by that distance, or in other words, it is the distance from the peak of a potential energy diagram to where the reactants initially started, or the potential energy of those reactants. And so if we look at that distance or that length there, that would be about 70 joules for where the peak of that graph is, 40 joules of where the potential energy of the reactants is. So 70 minus 40 is 30 joules, and that would be the activation energy of this particular reaction. But let's talk about what that actually means. These reactants here just don't magically become products. They have to absorb some amount of energy to break their bonds. Once their bonds are broken, then they can go and form the products. But the amount of energy needed to break those bonds is the amount of energy absorbed, or the activation energy. So underneath here, I'm going to say the amount of energy required or needed to break the bonds of the reactants. So it's how much energy is needed or required to break the bonds of the reactants so that they can eventually form products. And for this particular example, it would be 30 joules. Okay, next we're going to talk about activation complex, which a lot of students can mix up or confuse with activation energy. Activation energy is already labeled on the potential energy diagram above. It's what we did on the previous slide, and it's this distance right here from where the reactants start, or the potential energy of the reactants, to the peak of this graph. Activation complex is just at the very peak of this potential energy diagram. That is the activation complex. And so it's an intermediate stage where reactant bonds have broken, but the new bonds have not yet formed. So it's kind of like a jumbled mess of particles. It's neither reactants nor products. And if I were to ask you to give a numerical value of that activation complex, it is going to be 70 joules. And it's always going to be the most energy present in a particular reaction or the peak of this potential energy diagram. Now, two other things that are really important to understand is, in order for bonds to break and this activation complex to be reached, two things have to be true about the collisions of these particles. When particles collide, their bonds break, but they have to have two important characteristics of those collisions. First, particles must collide with enough speed or energy. And so when those particles are moving around in a particular substance and they're absorbing energy, they have to absorb enough energy in order to hit or collide with enough speed or energy. And so that is the first stipulation of those collisions. The next stipulation is going to be that the particles collide at the correct angle or orientation. So what that means is, if you have two particles here, you need a direct hit or direct collision in order for those bonds to break. If you have a particle here and a particle here, and this particle barely collides or barely hits the top or edge of that particular other particle, then bonds will not break. They need to hit directly with one another in order for those bonds to break, and they also have to hit with enough speed. And so that will be seen on the Schoology assignment, so make sure you understand those two stipulations about the collisions and what needs to happen with those collisions in order for bonds to break. Okay, next we're going to talk about the heat of reaction, and this is arguably the most important part of these potential energy diagrams, and it is the net energy exchange of the reaction. And this can be very similar to our discussions on Q or delta H. And you'll see the heat of reaction be symbolized as delta H quite a bit, and that means enthalpy. And we've talked about that term before. This is the enthalpy, delta H, or heat of reaction of the particular reaction. It's how much total energy is exchanged in the reaction. And that is always going to be the distance from your products to your reactants. That is delta H, or the heat of reaction, or enthalpy of the reaction. And you're always going to want to do your product's potential energy minus your reactant's potential energy, because the sign of the particular answer that you get will definitely matter, and we'll talk about why that is. And so here we're going to do 20 minus the potential energy of our reactants, which is 40. So 20 minus 40, and we are going to get a negative 20 joules if I were to ask you the overall delta H, or heat of reaction of this particular reaction. Now, the negative sign there is very important. This is a negative energy exchange. And if we have a negative energy exchange, if you remember, that negative sign means that the reaction is exothermic, meaning more energy is released in this particular reaction than is absorbed. Therefore, we term it as exothermic, which is why we have a negative delta H value. The last part or piece of these potential energy diagrams is called reverse activation energy. And you can see it symbolized as reverse E subscript A. That just means the reverse energy of activation, or reverse activation energy. And it is how much energy is released in the reaction. So if you see up above, we have everything that we've talked about already labeled on there, But the reverse activation energy is going to be this distance right here. The distance from your products to the peak of the particular graph. That is going to be the reverse activation energy. If you remember, the activation energy was from the reactants to the peak. The reverse activation energy is going to be from the products to the peak of the graph. And so that would be solved by doing, the peak is 70 minus 20. 70 minus 20, you're going to get about 50 joules for the reverse activation energy. Now, on top of being in the amount of energy that's released in the reaction, the true definition of reverse activation energy, which is very important, is that it is the energy required to break the bonds of your products, which is essentially opposite of activation energy. Activation energy is how much energy is needed to break the bonds of the reactants. Reverse activation energy is going to be how much energy is needed to break the bonds of the products. And it is going to be this distance here from the products to the peak of the graph. Now, that might seem a little funny. Why would we be concerned with the bonds of the products being broken? Well, we're going to learn about next unit in equilibrium that sometimes reactions can go in both directions. And so the activation energy is how much energy is needed for the reactants bonds to break to form products. The reverse activation energy would be how much energy is needed to break the bonds of the products and form those reactants once again, because sometimes these reactions can go in both directions. The last thing that we really want to hone in on is knowing whether, by looking at a potential energy diagram, the reaction is endothermic or exothermic. And every potential energy diagram is going to be different and look different based off of the particular reaction that it's representing. And so here I have two different graphs. We'll say this is graph 1, and we'll say this is potential energy diagram, or graph 2. And if you look at those, both look different, and that's because one is going to represent an exothermic reaction while the other is going to represent an endothermic reaction. Well, how, by looking at it, can we determine that? Well, there's actually a couple of ways. And way number one is, here is the potential energy of the reactants. Remember, the bottom line is the potential energy of the products. Well, if the potential energy of the reactants is greater than the potential energy of the products, it is going to be an exothermic reaction. Versus if the potential energy of the reactants is less than the potential energy of the products, we're going to say that it's an endothermic reaction. So that's the first way that we can tell whether it's exo or endothermic. The next way we can determine this is by looking at the activation energy and the reverse activation energy. Remember, this distance right here from the reactants to the peak of that graph is called the activation energy. And this distance right here from the products to the peak is the reverse activation energy. Well, if the activation energy, how much energy is needed to break the bonds of the reactants, is less than the reverse activation energy, how much energy is needed to break the bonds of the products, then it is going to be an exothermic reaction. And you can think of it as, this is how much energy is absorbed, this is how much energy is released. Well, more energy is released, therefore it's an exothermic reaction. On the other hand, here is our activation energy of our other reaction. This is the reverse activation energy, and this time the activation energy is greater than the reverse activation energy. Therefore, it would be an endothermic reaction. It's another way of showing if it's endo or exothermic. This is how much energy is absorbed. This is how much energy is released. More energy is absorbed, therefore it's an endothermic reaction. Now, going along with those 2 points, we can also decide which bonds are stronger, the reactants or the products. Here are our reactants. Here are our products. And activation energy is how much energy is needed to break the bonds of the reactants, versus reverse activation energy is how much energy is needed to break the bonds of the products. Here, more energy is needed to break the bonds of the products, so our products bonds would be stronger. Because more energy is needed to break those particular bonds. The reverse activation energy is higher. Versus on this other graph, this is our reactant potential energy. These are our products. This is how much energy is needed to break the bonds of the reactants. This is how much energy is needed to break the bonds of the products. More energy is needed to break the bonds of the reactants. The activation energy is higher than the reverse activation energy. Therefore, the reactants bonds are stronger. Because more energy is needed to break those bonds of the reactants for that particular potential energy diagram. Now, the last way we can determine if something's endo or exothermic is by calculating delta H. And if you remember, delta H is going to be equal to your product's potential energy minus your reactants potential energy. So I'll go ahead and do that for potential energy diagram number 1, or the one on the left. Here are our products. Here are our reactants. And so if I do products minus reactants, that would be 20 minus 40. That equals negative 20 joules. And if your delta H is negative, then you know that it's an exothermic process. Now with our other graph, graph number 2, here are our products, here are our reactants. And if I calculate delta H this time, I'm going to do products minus reactants. That'd be about 50 minus 40. That gives me a positive 10 joules. That is the delta H. And if delta H is positive, then you know more energy is absorbed and it's an endothermic process. Okay guys, that wraps up our stuff on potential energy diagrams. I miss you all. I hope all is well. And as always, if you have any questions, please do not hesitate to reach out. All right guys, I'll talk to you later.